Hello and welcome back to Calculus 3, section 13.4 on cross product. So this is yet another way to multiply two vectors, and this time the product, or the answer to the product, is going to be another vector. And it's going to have special properties, and it's going to be very important. So the skill of calculating the cross product is important. Let's first take care of that. Before we calculate anything, I have to say that the cross product works only for certain dimensions. So cross product works in particular, this case works for a 3-dimension, right, 3D, and then 7D, and then there are certain dimensions that support cross product and a lot of others do not. So we will only use it for 3D because we don't consider any other dimensions other than 3 and 4D and 2D, right, in this class. So we will use this only in 3 dimensions. So we use cross product for 3D vectors. So that's that part. Now let's take a look at the way they calculate. So vector u is going to be given with u1, u2, u3, and vector v is going to be given as v1, v2, v3. So these are our vectors. Now here is the way to compute the cross product u cross v. For this we will use matrix to set up, and then we are going to solve the determinant of that 3x3 matrix, break it down into 3 2x2s, and then finally get the answer. So we start by the first row is ijk. So first row is ijk unit vectors. Good one. The next one is your first vector that you're multiplying, so u1, u2, u3. And the third row is the second vector, v1, v2, v3. So that's the setup. And now we are going to compute, we are going to break this into 3 2x2 matrices. So now, please look at this. We're going to take vector I, and when you put I down, that will eliminate a row and a column, leaving u2, u3, v2, v3 as a matrix to deal with. Now, minus j, you have to remember it's a negative there. You eliminate row and a column, and what's left is u1, u3, v1, v3. And finally, plus k, eliminate row and column, u1, u2, v1, v2.
Why is j negative? Just because?
So you can get confused and miss it and then lose on the grade.
Sounds good.
Ask him, he's in linear algebra.
Just started it.
Yeah. All right, so now we need to solve the determinant of each of these matrices. And the way we calculate those, you can place this to calculate each one of the matrices. You will multiply diagonals and then subtract them. I like this because if you look at the center over here, you see a little multiplication symbol right there. There's a multiplication symbol. So U2 times V3, and this is flat, so that's like a minus. Oh, I can't see it. So as you go down diagonal, it's U2 times V3 and then the minus, and then V2 times U3. Cool, huh? All right, let's do this. So I times U2 V3 minus V2 U3 minus J U1 V3 minus V1 U3 plus K U1 V2 minus V1 U2. And then you box this. That's the way we compute. Clearly this is ijk, so it's a vector. This is a vector. It's a good warm-up for the rest of the course.
One of these problems take forever.
All right, so let's go vector u 1 3 4, vector v 2 negative 6, and what's a good number?
5.
5. Thank you. Well, I don't want to. I'll write these on the board as well, so because I need you guys to see the process. So 1 3 4 for you, and v is 2 negative 6 5.
Finding u cross v or v cross u?
U cross v. It's not commutative, but it's very close to being commutative. We'll talk about it. Oh, there she is. She's close to you. Yeah, I get it.
Negative. J is negative.
Well, it's
Well, if you make it plus J.
Yeah.
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 All right.
Do we have to write the whole, like,
No. If you are able to actually solve this by looking at it, fine.
okay.
Because it can be done, right? When you eliminate the first, that's 15 plus 24, and you're done, right? So you can actually, if you just write these two one above the other, you know that for I, you are ignoring the first ones. So 3 times 5 is 15, minus and minus gives you plus. So 15 plus 24 is 39. So the first coordinate is 39i. You can do it by looking at it without going through this huge process, but I will go through the huge process. So, yes?
Would you care if we left it in terms of I, J, and K?
No. You can either do the vector with the spiky brackets, like that, or you can use the IJK, whatever. Whatever makes you happy. It's like, United Airlines. Your happiness is our primary concern. You cross the line. Then, U cross V is I, J, K, and since U is first, the 1, 3, 4, and then 2, negative 6, and 5. So I, and we have 3, 4, negative 6, 5, minus J, 1, 2, 4, 5, plus K, 1, 3, 2, negative 6. So now, I, that's 15 minus negative 24, minus J, 5 minus 8, plus K, negative 6 minus 6. We can use either IJK or spiky brackets. That's 39, positive 3, and negative 12.
Oh, yeah. I didn't make those explicit.
Yeah, it's a negative. Yeah, minus. Yeah. Please practice this a lot, because this becomes a margin, calculation in the margin to find stuff that we actually need. So cross product is just going to be a tool. I understand that this is not the same level as memorizing 8 times 2 is 16, but that's the purpose of it, actually. So it's just a tool. This is not the end goal or learning outcome of a course. It's just a tool that needs to be quickly computed when needed for the rest of the problem. So please practice this. Now, I'm going to immediately write over here, because these are not commutative, that V cross U, if I swap this, all of the signs will change. So negative 39, negative 3, and positive 12. And I'm going to write the property that U cross V is the same as negative V cross U. So it's anti-commutative. What you get is, if you swap it, you get a negative sign. we will understand why when we get to the point. So now we know that the cross product exists. We know that the cross product is meant only for certain dimensions, and the only one that we care in Calc 3 is the throw-dimensional one, so we'll just focus on that one. And we also know that it's not commutative, but it's close enough. Now, we also want to write the formula that calculates the angle between two vectors using the cross product, but then let's not use it because we have the dot product, which is much faster, right? So the cross product will be the same magnitude times magnitude, this time times sine, okay? So the magnitude of u cross v is equal to magnitude of u times magnitude of v times sine of angle theta between these. And now, when magnitude of u cross v is equal to 0, u and v are parallel. If and only if u is parallel to v. Parallel. So that one runs parallel to the two vectors are orthogonal if they are perpendicular. In this case, if the dot product is 0, then two vectors are orthogonal. If the cross product is 0, then two vectors are parallel. Let's put the properties. Property number 1, I already have that one. U cross V is negative V cross U. Then we have associative property, which says that AU cross BV is AB U cross V and two distributive properties, U cross V plus W is U cross V plus U cross W. And because it's not commutative, we also have to say that U plus V times W, I mean not times, cross, it's times, but is U cross W plus V cross W. If you are interested in proving any one of these, just replace all of your U's with U1, U2, U3, V's with V1, V2, V3, and W's with W1, 2, and 3, and then just grind through calculations. You will see that left side equals the right side. That's the way to verify all of these. And now, the most important thing, which is why we actually bother with a cross product. Why is this thing so important? What happens is when you take the cross product of two vectors in space, whatever those vectors, so I have these two vectors in space. When I do the cross product of these two, I am going to get vector that is perpendicular or orthogonal to the plane that these two vectors create. See, if I have two vectors, those two vectors have 3 points. There is a point where these vectors are joined, and each of the terminal points for each of the vectors. That's 3 points in space. 3 points in space define a plane. 2 points in space cannot define a plane because it's wobbly. 1 point in space also doesn't work, it's wobbly. 4 points is already too much because we can do with 3. So if you have 3 points in space, you can define two vectors, and those two vectors would define the plane. Now, when you do the cross product, when you take the cross product of those two vectors, the vector that you get as the answer for the cross product is always perpendicular to the plane that those two vectors created. What you are getting is what we call a normal vector to the plane. Whatever way the vectors are oriented to create the plane, the normal vector is always perpendicular. The entire plane will be expressed through a single vector, which is the normal vector. And now, we'll have a separate lecture on planes, so that will be repeated and restated many times. But what I want you guys to quickly understand here is that U cross V gives me this guy, and V cross U gives me that guy, right? The one that is pointing. And they're the same vector, just opposite direction. And you saw me earlier just change the signs on the vector. That's the same magnitude, and it's on the same line, it's just the other way. So U cross V will give you the one side of the plane, and V cross U will give you the normal vector on the other side. And as you can see, as always, all of that just clicks together in one shot. So here, in blood, cross product between two vectors gives us a orthogonal vector called the normal vector. Usually we have lowercase n as a vector, right, with the arrow. The 2 over the top. Very good. There we go. We got it. So we know how to calculate. We know we'll do the application later. Is there anything else? That's it. Okay. So we can now talk about the application. I heard that.
What?
I heard that.
There's a whole other lesson.
I know.
Okay.
Oh, yippee-ki-yay.
So, what is the application? The cross product can give us the area of the parallelogram that would create that the two vectors create. So if I have a vector u and a vector v, do you want my line?
Take my one off.
So if we have two vectors u and v, then the shape is called a parallelogram, and area is given as absolute u cross v. So you find the magnitude, and that will compute the area of the parallelogram. There we go. You can cut that in half if you want the area of the triangle, right? So you can play with those geometric properties if you're interested. Physics, that's why we're all here. Cross product, what is it used for? It's used for calculating the torque, and torque is the force that operates in circles. So if you think about the wrench, so you have, let's see if I can, yeah,
Wrench.
boss. All right, so now we're going to put a nut over here. There we go. Perfect. So now you apply force here. There is the radius r, and what happens here is this turns with what we call torque. So the torque is the force that is like, it's a twist, right? So it turns. Now this is one of the examples. So this is one of the examples, and then we have the force, the torque. I don't have to be dramatic. Torque is equal force cross radius. And that gives us that calculates the torque. Another one that you can consider as an example, I'll just say door. We're going to take a look at this door from the top view. So this is the wall. This is the wall. And now you're going to have a hinge over here and the door. So when you push at the handle, so you are applying force this way. This is again top view, right? Top view. As you apply the force on the handle, the door swings open. Now, how many times have you pushed on the wrong side of the door, right? How many times have you pushed right here and nothing happened? So why nothing happened? Well, if you are pushing at the hinge or very close to the hinge, right, the radius that you are multiplying by is either 0 or near 0, which is why you are not creating the torque to open the door. Make sense? So you always want the handle to be as far, the full length of the door on the other side. And you can try the experiment as you are leaving the classroom. If you're pushing the middle of the door, it's harder than if you're using the handle. And if you're pushing right next to the hinges on the completely opposite side where the handle is, it is very difficult to open the door. Bye.